Can you see the presentation clearly?
Yes.
All right. Okay, I'll start right away. Good evening, distinguished judges and fellow participants. My name is Andini Kalea from State Senior High School 2, Depok, Indonesia. And today I am honored to present my research entitled Design and Development of an Integrated Multi-Parameter Motorcycle Brake Monitoring and Warning System for Detecting Disc Overheating, Brake Fluid Depletion, and Brake Pad Wear. First of all, Indonesia is home to more than 145 million motorcycles, making them the country's most widely used form of transportation. That also means millions of riders place their trust in their braking systems every single day. Now imagine you're one of them. Picture yourself riding your motorcycle home after a long day. Everything feels completely normal. You approach the red light, you squeeze the brake lever, and nothing happens. And within seconds, a normal ride becomes an accident. The frightening part isn't that the brake failed. It's that the brake had probably been deteriorating for weeks or even months, yet the motorcycle never warned you. Unfortunately, this isn't just a hypothetical situation. In 2025, my own mother experienced a motorcycle accident caused by brake failure. That experience made me ask one simple question. What if the motorcycle could warn riders before the brakes actually failed? But before I designed any solution, I first asked, what causes brake failure? From the literatures I've read, I identified three major brake failure causes. First, brake disc overheating. Continuous overheating above 200 degrees Celsius could cause thermal fatigue and brake fade to occur. And second, we have low brake fluid volume, which compromises hydraulic pressure and can lead to complete brake failure. And third, we have brake pad wear, where progressive friction material loss reduces contact area until catastrophic metal-to-metal contact occurs. And here, can we notice that there's something interesting here? That all three problems develop gradually, yet motorcycles don't tell us anything about them. So I asked myself, if motorcycles can already tell us when fuel is running low, why can't they also tell us if we're about to lose our brakes too? But before I jumped into my research, my next question was, have researchers already solved this problem? I reviewed previous studies, and although there are many excellent systems developed, nearly all of them monitor only one brake parameter at a time. But brake failure is rarely caused by just one component. A doctor wouldn't evaluate your health by checking only your blood pressure. Likewise, monitoring only brake temperature or brake fluid cannot provide a complete picture of brake health. To address this gap, this research focused on the design and development of an integrated prototype capable of monitoring brake disc temperature, brake fluid level, and brake pad wear simultaneously. Since no similar integrated prototype has been reported in the literature, this work also serves as a preliminary study, establishing the foundation for future development and validation of integrated motorcycle brake health monitoring systems. Here, we have the prototype design and system operation. We can see the hardware overview. After defining the objective, the first step was developing the prototype itself. I initially assembled the entire system on a breadboard to verify the circuit and software before producing the final enclosed prototype. The Arduino Uno serves as the brain of the system and receives information from three sensing modules. First, the MLX9614 for disc brake temperature, the K0135 sensor for brake fluid level, and the three embedded conductive wires for brake pad wear. Together with the OLED display, LED indicators, buzzer, and micro SD module, these components form one integrated monitoring system. Here we have the sensor placement and purpose and thresholds. Each sensing module was then installed according to its intended function. For example, here we have the MLX9614 infrared temperature sensor that measures the brake disc temperature without direct contact to detect overheating, placed in front of the disc brake. And then there's the K0135 liquid level sensor placed in the brake fluid reservoir. And we have the three embedded 18 AWG conductive wires integrated into the brake pad to detect progressive brake pad wear as the friction material gradually becomes thinner. Every sensor is continuously compared against threshold values obtained from previous literature, allowing the system to classify conditions as normal, warning, or critical. Once installed, the prototype operates in 5 simple steps. First, the sensor collects real-time data. Second, the Arduino classifies every reading according to its threshold. Third, the rider immediately receives the visual and audible warnings through the LED indicators and buzzer. Fourth, the live data is shown through the OLED display, which the user can switch screens using the push button. and have the different screen modes. And then finally, every measurement is automatically stored on the micro SD card for later analysis. And here we have the hardware assembly. After validating the electronics, the system was permanently assembled inside a protective casing. The Arduino Uno display, OLED display, LEDs, buzzer, and power regulation circuit were integrated into the main enclosure, while the sensor were connected using an extended wiring for installation on the motorcycle. Finally, the completed prototype was installed onto a Honda Vario 150 ESP, which served as a test vehicle throughout this preliminary study. Designing a prototype is only half of the research. The next question is, does it actually work? To answer that, each subsystem was evaluated under its intended operating conditions. Overall, brake monitoring, brake pad detection, and all output components operated successfully. Although the brake fluid sensor accurately detected the normal and critical states, but showed lower reliability in the intermediate warning range due to its nonlinear sensor response. Meanwhile, the warning and critical temperature were for the disc brake temperature were not evaluated because the available physical references temperature never exceeded 150 degrees Celsius. And we have the final test, which is for the real-world testing. Can the complete prototype maintain stable operation under real riding conditions? And the answer is yes, but although there is one limitation, which is for the brake fluid monitoring, which is limited because the motorcycle, due to the physical design of the reservoir cap and the corrosive nature of dot 3 and dot 4 brake fluid for in the motorcycle. And here we can see, did the prototype answer the problem? Yes, but with different levels of confidence for each failure mechanisms. Brake overheating and brake pad wear were successfully addressed through reliable monitoring and early warning. Brake fluid monitoring successfully identified critical conditions, although warning stage still requires further calibration. And most importantly, also the brake pad wear also successfully can detect the different threshold values. And most importantly, this research demonstrates that 3 independent brake failure mechanisms can be integrated into one real-time monitoring system instead of being monitored separately. And here we have the future work and final takeaway. At the beginning of this presentation, I asked you to imagine approaching a red light and suddenly realizing your brakes no longer work. This research began with one simple question. Can motorcycles warn riders before brake failure becomes an accident? This preliminary study demonstrates that the answer is yes. Future work will focus on validating thermal measurements using calibrated infrared instruments, improving brake fluid sensing accuracy, integrating brake fluid monitoring during real riding, evaluating brake pad detection under controlled wheel speeds, and establishing internationally standardized references thresholds for integrated brake health monitoring. With these improvements, this prototype can continue evaluating from a research prototype toward a practical motorcycle safety system, because ultimately the safest brake failure is the one that never becomes an accident. Thank you very much for your attention. If you find this research meaningful, I would greatly appreciate your support by voting for my poster, and I would now be happy to answer any questions. Thank you.
Thank you. Perfect engineering work. Any question? Yeah, I have a question. First of all, is your mother okay?
Yes, my mother's okay. Thank you for
What a
asking.
relief. And my second question, could you please elaborate a little bit more? How was pad wear monitored? Like,
The brake pad monitor?
yeah, how was brake pad wear monitored? Like, what did you use to monitor it?
Okay. Here I can show you my prototype. We can see this is the brake pads, and in the brake pads I drilled 3 different holes, and you can see that there's 3 different wires. And in the brake pad there is the 100% wire, the 50% wire, and the 25% wire, and they're all placed on different depths. So the disc brake is given a ground connection continuously, where the Arduino reads the ground connection as low. So when the wires touch the disc brake, that means it will read as low. And when it reads as low, let's say the 100% wire, or let's say the brake pads are still full or they're still normal, that means the 100% wire should always be touching the disc brake, and it will signal the Arduino that it's low. So it's like saying, hey, it's still full. But as the brake pads progressively loses its thickness, or it sheds its thickness, then it will reach the 50% wire, and the 50% wire will also touch the disc brake, reading low input 2 to the Arduino. And when it's finally um, none left, or like the brake pads are empty, or like this thick, or like it's already super thin, then the last wire, the 25% wire, will touch uh, the disc brake and read as low in the Arduino. Does that make sense?
Yeah, that makes perfect sense. But can you imagine a better way, maybe, to measure the thickness of a brake pad? How reliable this method is that you currently used?
Currently, I cannot say it's fully reliable because it uses three different specimens to test it. So I tested it on 7 millimeter, and then 6 millimeter, and a 5 millimeter. So it's heavily dependent on the specimen's thickness itself. Not I did not measure the how it gradually wears down. And because this is still a preliminary study, which also becomes a limitation in this study, and which I will improve in future work. But I can say the literature that I referenced this to, uh, what they achieved, they couldn't achieve it, the implementation to the brake pads right away. They made a prototype of the brake pad using different materials that can actually gradually wear down, and they scaled up the wires. So technically, this whole prototype is kind of impossible to be done, implemented like this, but I made it possible, but it's not really reliable, or should be implemented as commercially yet, which is why uh, have written this down as a limitation and to be worked on in future work.
Okay, thank you very much.
Yep.
Great project and presentation. And what factors can falsely trigger your system?
Oh, okay. So what factors might falsely trigger my system? Is that the question?
Yes.
Okay. So first, I have analyzed that in Indonesia, it's very hot, right? We live in a tropical country, and the problem is the district temperature here. You know how like in a in a summer day, the heat from the sun can reach the disc brake and gives off false temperature readings before it actually reads the dangerous or the threshold temperatures, which can cause um, false alarms. And another thing is for the fluid sensor, because it isn't tested on real riding conditions, when we're riding motorcycles, the brake fluid will slosh around, and that can mess up the volume reading accurately. So for now, I have only analyzed those two false alarms so far. Does that answer your question?
Yes, thank you.
Do you have any question, Nikita? No? Okay.
No.
Okay. My question is, what is the estimated false positive rate for the brake fluid level sensor when the motorcycle is on the step incline or step slope?
Oh, that I cannot answer because again, I have shown you in the limitation that I did not integrate the brake fluid monitoring because due to the physical design of the reservoir cap on the motorcycle and the corrosive nature of dot 3. So I guess you can imagine, since the brake fluid is so corrosive, so if any of the liquid comes out, it will take off the the painting off the motorcycle, and it's also corrosive to the skin. So the reservoir cap is actually, it has 5 layers, and I have not managed to be able to integrate it, which is why I also included this in the limitation for future work too, to be able to integrate or make a custom reservoir cap so I can integrate this fluid level sensor. Does that answer your question?
Yeah, sure. Okay, thank you.
Yep. Is my presentation over?
Oh, yes, if there are questions, you can close your presentation. Thank you very much.
All right. Thank you so much, judges and the YSF people, to give me this chance to present. And thank you.
Okay, thank you. Good luck. Well, we have 2 projects left from Indonesia.